Have you ever really stopped to think about what connects that smartphone in your pocket to, say, a handful of sand from the beach? Well, today we are diving deep into the magic that turns a simple rock into the absolute superpower behind every piece of modern technology. We're going to go from the ground up and really understand the tiny, tiny components that basically run our entire world. So let's kick things off with a bit of a puzzle. Just look at your phone for a second. Now, picture a plain old rock. I mean, on the surface, they couldn't be more different, right? But what if I told you they share a deep, fundamental secret? The answer is the key to, well, everything we're about to get into.
And the answer is pretty much everything. Seriously, at their very core, they're both built from silicon. That simple rock, or the sand that it eventually breaks down into, is the source material for the one element that has completely reshaped human history. Today, we're going to see exactly how that amazing transformation happens.
So here's our roadmap. First, we'll look at what makes silicon so special. Then, we'll learn how to give it some incredible superpowers through a process called doping. After that, we'll start building our first real components, these one-way streets for electricity called diodes. Then, we'll use those to tame AC power in rectifiers, and we'll wrap up with maybe the most important invention of the 20th century, the transistor.
You know, the best way to think about this is like this. A copper wire is basically a superhighway for electricity. The traffic is always flowing. Rubber, on the other hand, is a brick wall. Nothing gets through, ever. Silicon is the real superstar because it's like a programmable gate. It's not always on, it's not always off. We get to tell it when to conduct electricity. And that simple ability to control the flow, well, that's the foundation of everything. But here's the catch. Pure, perfect silicon is actually a pretty terrible conductor. It's too perfect, too stable. To make it do what we want, we have to mess it up a little bit. We have to intentionally add some impurities, and this process has the awesome name of doping. Doping is really the secret sauce. We take that pure or intrinsic silicon and we mix in these tiny, super precise amounts of other elements. It's this intentional impurity that changes everything. It turns a boring, stable crystal into the flexible workhorse of modern electronics. And this whole process creates two very different flavors of silicon.
So these two flavors are called N-type and P-type. The absolute best way to picture this is to think of a dance floor. For N-type silicon, we add something like phosphorus, which brings extra electrons to the party. It's like having a few extra dancers show up who don't have partners. They're just free to move around. For P-type, we add boron, which creates holes, or shortage of electrons. These are like empty spots on the dance floor that all the other electrons are just itching to jump into.
Okay, so what happens when we bring these two different dance floors together, when we join the N-type and P-type silicon? We create something incredible, a PN junction. And this simple meeting point is the heart of a component you are going to see everywhere, the diode. And a diode is, for all practical purposes, a one-way street for electricity.
So right where these P and N materials meet, the extra electrons from the N side immediately rush over to fill those empty holes on the P side. This creates this neutral zone right in the middle called the depletion layer, which acts like a small barrier or maybe like a toll booth. And to get current to flow across this barrier, you have to pay the toll. For silicon, that toll is pretty much always about 0.7 volts.
And that 0.7 volt drop, that's not just some abstract theory. It's a fundamental number you're going to use constantly when you're designing or analyzing circuits. So let's just walk through a classic exam-style problem. Let's say you've got a 5-volt power supply, a diode, and a 470-ohm resistor. How in the world do you figure out what's going on in this circuit?
All right, let's break it down. It's actually a pretty simple three-step process. First things first, we have to pay that diode's 0.7 volt toll. So you take your 5-volt supply, you subtract that 0.7, and that leaves 4.3 volts for the resistor to work with. Okay, step 2. Now we just use good old Ohm's law to find the current. Remember, I equals V over R. So 4.3 volts divided by 470 ohms, that gives us about 9.15 milliamps. And finally, step 3. How much power is the diode itself burning off? Well, we just multiply its voltage drop, that 0.7 volts, by the current we just found. And that gives us a tiny 6.4 milliwatts. See? That's all there is to it.
So what's a big real-world use for this little one-way gate? Well, one of the most common jobs is happening inside every single one of your power adapters. Yep, your phone charger. See, the power coming from your wall is alternating current, or AC. It's constantly switching direction. But your phone and all your electronics, they need stable direct current, or DC. Diodes are the absolute key to making that conversion happen.
Now, the most basic way to do this is with what's called a half-wave rectifier, and it is incredibly simple. You just use one diode. Since that diode only lets current flow one way, it lets the positive part of the AC wave go right on through, but it completely blocks the negative half. It just chops it right off. Okay, for anyone studying this stuff, pencils out. This is a huge takeaway. These formulas for calculating the average DC voltage you get from a half-wave rectifier are fundamental. You can see that the DC voltage you actually get out is only about 31.8% of the peak AC voltage. It's not super efficient, but it's a foundational concept, so you'll definitely want to remember this one.
Now you can imagine, just blocking and throwing away half of the power isn't exactly efficient. So a much better design is the full-wave rectifier. Instead of just tossing out that negative half of the wave, it uses a clever arrangement of diodes to flip it over, turning it into another positive pulse. This way, we get to use the entire AC signal. Much better, right? And just as you'd expect, the math shows this big improvement. Because we're now using both halves of the wave, the resulting DC voltage is exactly double what we got before. We're now up to around 63.7% of the peak voltage. Again, for anyone studying, comparing these two sets of formulas side by side is absolutely crucial for understanding efficiency. This is another one for the flashcards.
Okay, now we're ready for the next big step. If a diode is a simple one-way gate, then a transistor is like a fully controllable electronic valve. This is where things get really, really powerful. A transistor allows a tiny, tiny electrical signal to control a much, much larger one.
To really get how it works, let's just tell a quick story. I want you to imagine a huge reservoir of electrical current, just sitting at a terminal we call the collector. It's just waiting, ready to flow down to another terminal called the emitter.
But it can't. There's a problem. In between the collector and the emitter is this thin little layer called the base, and it acts like a massive locked gate, holding all of that potential current back.
And here is where the magic happens. All you have to do is send a very, very small current to that base. That tiny current acts as the key. It unlocks the gate, and suddenly, that huge current from the collector can just flood right through to the emitter. A tiny key opens a massive floodgate. And we can describe that incredible floodgate relationship with a beautifully simple formula. The large collector current, or IC, is equal to the small base current, IB, multiplied by a factor called beta. Beta is just the transistor's current gain, and beta can be 100 or even more, which means our tiny little key current gets amplified into a collector current that's 100 times larger. This principle of amplification is what makes all of our modern computing possible. So let's just step back and look at the amazing toolkit we've just put together. We started with some basic raw material, we doped it into N-types and P-types, we smashed them together to create diode one-way gates, we used those gates to convert AC to DC, and finally, we built a transistor to act as a current amplifier. These right here are the absolute fundamental building blocks of all modern electronics.
And that really leaves us with a final thought to chew on. The core idea of a transistor is amplification, using something small to control something big.